Okay, let's get started. So far we have done with our first unit that talks about computational logic and sequential logic on the circuit level. So that's for many of you it's a review, but for many of you it's the necessary knowledge to learn computer architecture so that you can deal with more complex topics. Starting from here, we're going to talk more about architecture on a higher level. And starting from this lecture, we're going to try to use 2 to 3 lectures time to talk about computer architecture simulation. Especially, we're going to talk about the Akita simulator framework. So the goal is for you to know how to use a simulator framework, and so that you can work on your future assignment by implementing some simulation. So I find the best way to learn computer architecture is just to pretend that yourself is the designer. So you design the architecture on your own while you are implementing a simulator. When you are implementing a simulator, just imagine, like, every time you know, well, how do I implement the simulator, right? Then how do you implement part of the simulator? So how do you implement the simulator? Then whenever I have this type of problem, how do I implement the feature? I just think, oh, how can a real hardware do this thing? If real hardware cannot do this thing, you probably shouldn't implement in this way in your simulator. Then basically, when you are implementing a simulator, you're putting yourself in the shoe of computer architecture designer. Just imagine, like, okay, if I'm the designer, if I were the designer, how I can design something, okay? So in this lecture, we're going to talk about simulation. Now, after the simulation, we're going to talk about the core architecture. Then we eventually go to the memory side. Okay, so computer architecture simulation. Okay, so why we want to do simulation? I even sometimes get some questions from experienced computer science researcher. Now, if they're not in the computer architecture domain, they think, oh, especially I'm working on the GPU simulation, they think GPUs are so widely available, why you cannot just use a GPU? Why you have to still implement a simulator? Then the quick answer is you want to verify your design ideas. You want to design some new architecture. But you cannot really. You want to design a new architecture. You have some new idea. You have some new algorithms. You want to validate your idea works. Then you cannot really build a new hardware, right? When you build a new hardware, see the cost of building these new chips is probably very small here, but this is 10 nanometer, 7 nanometer, and 5 nanometer here. So 5 nanometer here. See how much it costs to design and manufacture 5 nanometer chip. It's basically, as this data source, it says it's $542 million to produce a 5 nanometer chip. So that's basically beyond the capability of an academic researcher. Then you cannot really spend a lot of effort and resources to really manufacture a chip just to validate your idea. Even in the industry, they cannot really say, oh, a designer has an idea, let's just try to build a chip and see how it works. Internally, they have to use some simulator to first let their engineer to convince their administration, their executive team, so that this idea is workable, it's a reasonable design. Then they can start to make it into the product, then really produce it eventually. That's probably a few years, like from an initial idea to eventual product. That's probably a 5 years period that you may think that out of several hundreds ideas, probably only 1 or 2 are eventually selected. So they have to use a simulator to quickly rule out the ideas that does not work. Okay, so we want to use simulators to verify design at a very early stage, and during this process, we may want to do something like a bottleneck analysis. So if we run a program, we want to analyze what is the bottleneck. If you run a profiling tool, you may really not to get that low-level detail, cycle-by-cycle details, but simulator can provide you with more details. Headroom exploration is a very specific type of experiment that is very specific to simulator. For example, I want to work on something in cache, memory access, right? So I don't know if memory access is eventually profitable in terms of performance improvement. So what I can do is I can set an ideal case. I can set, say, memory access. Every memory access can be done within 1 cycle time. Now, last time we talked about like memory access can be hundreds to thousands cycles. If I set it to only 1 cycle, that's the most ideal case, right? In that case, if my performance only improved by 3%, that's pretty much saying the memory side is not a performance bottleneck. Now, if you keep working on that, it's not profitable at all. Then we can quickly rule out this research direction. Although I'm saying 1 cycle latency is probably too optimistic. So sometimes we may want to do, say, something like, oh, I want to have a limited size of cache, right? Something like this. So it's called headroom exploration, and it really requires complete architecture simulator that is a pure piece of software that we can do whatever we want. Even if you do something like FPGA-based simulation, you cannot do that. Now we have like a design space exploration. For example, we don't know what's the best cache size. Now we can scan through, say, 1 megabytes, 2 megabytes, 4 megabytes. Then probably you will see this type of curve. At the beginning, you're increasing the performance, but at some point, this is no longer a bottleneck. Then putting more resources will not increase your performance. Right? This is a design space exploration, and it's very important for computer architecture research. And this can also be easily done by a computer architecture simulator. The hardware algorithm evaluation, then we want to replace the hardware, like the algorithm run on hardware, then we can test the different algorithm. So everything related to simulation is we want to reduce the cost and quickly rule out the idea that's not feasible, like even without doing a low-level, RTL level, Verilog, or sequential logic level design. Okay, that's why we want to use simulation. So, and at the beginning, I want to talk about simulation methods. So in general, how we run simulation. So then there are many different ways to classify computer architecture simulators. So let's talk about all the terms that we're going to use, that you are going to encounter in the simulation domain. So last time we talked about, for 3 lectures before, we're talking about sequential logic, right? Sequential logic are basically digital circuit. It's a way of digital circuit organization that includes registers and combinational logic, especially when we consider synchronized sequential logic. That means there's a clock signal that is controlling everything, and all the state update. State means the data that is stored in the register. All the register state update happens at the edge of a clock, either rising edge or down edge. So that means if we can properly model all the state and model all the combination logic, then especially the combination logic are mostly deterministic, right? So if we can just simply repeat all this logic, then pretty much we can simulate the every cycle's behavior of a computing chip, right? So that basically we want to use this simulate the synchronous digital circuit by doing this. If you have different components, let's say each component is a combinational logic with its associated register, okay? Then we can simply do tick, 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 which a tick is an edge of a clock cycle. Then at every tick, we ask this combinational logic to update its state so that this register also updates its state, right? Next tick, every component update its state, update states, update states. Then eventually we can simulate any type of digital circuit. So that's a very high-level description of computer architecture simulation. Then you might find that is the end. Now we can simulate everything. Can we just simply do this and simulate all the digital circuit? And for many simulators and for very simple low-level like ad hoc simulators, and this is probably already at the end. That's good enough. But there are many constraints that prevent us from doing this thing. So let's talk about different type of simulations. So there are different type of simulations. What we're talking here is either RTL simulation or cycle level simulation. What is RTL simulation? Although we haven't talked about Verilog, but a Verilog is a descriptive language that is written to describe a sequential logic, a combinational logic, and its register state. So that's RTL, the register transfer level. So what is register transfer? It's basically you have a register, right? Then at every cycle, you pass the data, update the data, and either transfer back to this group of register or transfer to the next group of registers. That's why it's called register transfer level simulation. Then it's either at a cycle level simulation or RTL level simulation. But sometimes we want to pursue more higher level of accuracy. For example, if you really care about like the super low level detail about the latency of each gate, we may probably go down to the analog level simulation, like to consider if our voltage is good enough to drive like the next level gate. Say if one gate is controlling 10 other gates, so probably our voltage is not high enough to control all this gate. So in this case, if we care about this information, we do analog level simulation. Then on the other side, higher than cycle level simulation, we can even do higher transaction level simulation. For example, if I know a matrix multiplication will take 1 second to run, and I'm going to run 10 matrix multiplications, now quick simulation tells me that the whole program will run 10 seconds, right? We don't really go cycle by cycle low level detail. We can go at a higher level, that's a transaction level simulation. So we can make a very detailed comparison about these different level of simulations so that you can make a good trade-off between, say, or which level of simulation that we want to use. For most of the time here, in this course, we're talking about cycle level simulation. Okay, so there are many different metrics that we can, dimensions that we can compare. So what's the incremental of the time, or what's a cycle in this type of simulators? Then these are cycle level, right? These two are cycle level. That means we are doing cycle by cycle. We only care about clock edges, right? But if you want to do analog simulation, then we probably need to do much finer granularity. It's still discrete time simulation, but we can break down the time into 100th of a cycle so that we can know how this voltage is eventually built up and how this voltage propagates through the cycles. In that case, we can calculate, if the signal propagates through the gates, have enough time to reach the next set of registers. Those are analog level simulation. The transaction level simulation are coarse grain time that can be seconds, tenths of seconds, can move really fast. Then another term that you may commonly hear is a cycle accurate term, a cycle accurate simulation. A few years ago, 5 years ago, people really liked this idea, or they like to use this term. What is a cycle accurate simulation? Then there's no common definition, but my common definition is, it's cycle level, and it's accurate. How can you know it's accurate? Is you have the RTL level information, but you have all low level information, but you just implemented this at this level. Okay, so it's accurate. So as I say here, the more you go towards that side, it's more accurate, right? But it's slow. On this side, it's fast but less accurate or less control about what's going on. Okay. So we need to make a trade-off and find the best place that we want to implement our simulation. Now, in terms of accuracy or fidelity, what type of accuracy that we can get? For analog simulation, we have voltage and current level accurate. Like the voltage, even at a finer granularity, now we know what's the voltage at any point on the wires. Then the RTL is binary accurate. That means, let's say if you want to transfer a wire, and on wire that's say you want to transfer a message, then on this message, you really need to care about what is the packet header, what each bit represents, so that you can send this information to the next stage, and next stage can parse this information. That's RTL level simulation. Then on cycle level simulation, since it's mostly implemented in software, we don't really care that much about bit level accuracy, binary accuracy. For example, if you write RTL level simulation, then you have a network, right? From A node to send to B node, there are several nodes in this network. You have to have a specific way to identify each node. Say this node is 1, 2, 3, 4, and 001, 002. Then you have to identify them and send it through the network. Now, if you are implementing a cycle level simulation, you can simply say, okay, that is my destination. And then just simply pass a pointer in the software, a reference to that element. So that is my destination. You don't really need to care, like I have to send 0006 as the identifier of that destination. And that's why at the cycle level simulation, the accuracy can be sacrificed a little bit for something that you don't really care, but it's much, much easier to program. Okay, then at the transaction level, basically we typically do time-only simulation. So there's no functional emulation. We do not care about the execution result. We only care about the time estimation. Then different level. For analog level, we typically do transistor or sub-transistor level modeling. Then for RTL level, we care about every gate. We need to know every gate and model the every gate's input and output. But we can assume that if it's a NOT gate, you can always simply invert the result. Now for that one, analog simulation, we may consider that this NOT gate may even not work, right? For RTL simulation, we always assume the gate works. Then for cycle level simulation, then we do not care about gate. We say, oh, here we need a multiplication. Now we just simply use a software to do the multiplication. We don't really care about gate. Now here we only care about the timing to be accurate. In terms of performance, we say on that side is slow, on this side is fast. So that's my personal experience about how slow they are. And analog simulation can actually be even more slower than this one. It's 10 to the 10 times slower. So that means what? So if you want to simulate 1 nanosecond simulation, then you multiply by 10 to the power of 10. 10 magnitude, that's basically 10 seconds execution. So you need 10 seconds to simulate 1 nanosecond real hardware execution, right? 10 seconds per cycle. Don't take that to literally. Different simulators scale can be different, just the magnitude. Okay, then RTL level simulation can be 1.1 10 to the power 6 to 10 to the power 8. And this one is 10 to the power of 4 and to 10 to the power of 6. And so what's the 10 to the power of 6? Then in general, we typically, when we do GPU simulation for a full GPU, large-scale GPU, then my personal experience is if you want to simulate 1 second real GPU execution, it takes typically a day or more. Okay, so that's a big difference. Then transaction level simulation. If it really depends on what's your transaction, but it can be as fast as real-time execution. Right? You say, oh, I know this action takes 3 seconds. Now I can use like a few milliseconds to simulate a 10-second action. It can be even faster than real time. Okay, so the slowdown actually determines that we cannot simulate like a scale at too large. So what's the scale that we can simulate? Then for analog simulation, we probably will limit us to a combinational logic level. So for example, when we design ALU, we want to simulate an adder or multiplication unit, division unit, or calculate log, sine, these type of operations, and just to verify if it can propagate signal to destination within the given time. Now for RTL level simulation, we typically can do 1 CPU GPU core. Then that's probably that's what we can do. Then at the cycle level simulation, then we can do probably one GPU, one machine with multiple GPUs. So I can tell you some experience that when we simulate graphics simulation, like the graphics means we're simulating a GPU that is rendering an image. So probably we can at most render a 1080p image, one frame of image being simulated within a day or a few days time frame. One frame. Okay, so one frame, if you want to play a reasonable game, that's 1/60 second, right? 1/60 second. So that's what we can simulate with cycle level simulation. Now with RTL simulation, you want to simulate a whole GPU to render a frame, it's generally impossible, even if you use FPGA. Use FPGA, the limit is not speed, it's not performance, it's the FPGA cannot really hold the logic of a GPU within one FPGA. You really need a lot of FPGAs. Then if you connect lots of FPGAs and they're connected with network, then it's actually much slower than using a single FPGA. So transaction level, we can do several tens of GPUs, hundreds of GPUs to a data center level simulation. Okay, then this is magic. What is magic? Magic is something that you want to simulate something that is impossible physically. Like something I was saying is the roof line or the headroom simulation, right? We want to simulate a limit cache. Now, can we simulate a limit cache at a different level? For analog simulation, you probably cannot even simulate the whole cache, right? So no magic. Magic difficult. Then it's possible. Then you cannot really simulate the whole like infinite cache, but you can simulate a much larger cache. You can slow down things, but you can do it, right? This one, like this is the magic point, right? If you want to add magic, you want to add a reasonable magic here. Then transaction level simulation, I say itself is magic. It's I wouldn't even say it's a simulation. It's more like an analytic model for performance. Then, okay, then more points. I should make 2 slides. Is that actually 2 slides? No, it's 1 slide. Okay, so energy estimation. So energy estimation is more and more important. Like when we design computer chips, energy is not about saving energy. It's about performance. If we have a chip that runs at 300 volts, if you can reduce it to 150 volts, you're not really saving energy. You will still run at 300 volts, but at a much faster speed, right? Much higher frequency. That basically means energy can translate to performance. So analog simulation is generally considered energy accurate, right? And this one, gate RTL level simulation is typically considered that we can have a good reasonable estimation of energy. So when you consider energy is typically consists of 2 parts. One is the static energy. It's basically your whole chip is consuming even if you're not running anything. Then the other side energy is the dynamic energy. Dynamic energy happens when you have a transistor that is flipping from a closed to open state. Whenever you flip, then you consume some energy. Then, so if it's a transistor flip, it's really data dependent, right? If you flip a lot of gates, flip a lot of register, it actually opens and closes a lot of transistors, right? So that's why RTL level simulation, if you want to have a very accurate level of estimate energy, then you probably want RTL level simulation. Then for this cycle level simulation, it can be an approximation of model. For example, I can estimate 1 bit if I send through a wire, and I know this wire is how long, then I can say how many picojoules that it takes to transfer 1 bit. So that's basically an estimation or a model. Or like a cache heat takes how much energy, cache miss takes how much energy. That's basically a linear regression based or different type of regression based model. Then this one is pretty much energy modeling. Then it's very hard to say we're accurate. Then it needs a lot of assumption to make transaction level simulation to estimate energy. Okay, then the input. Now here, for analog simulation, we typically use a netlist input. Netlist input is, you can consider it's a graphic representation that say, okay, this point connects to this point, here is a transistor, then you describe this type of things. Then for RTL simulation, we provide Verilog or VHDL, or it can actually be converted back to netlist, and we still simulate at the netlist level. Then cycle level simulation, most of cycle level simulation these days are implemented use C or C++, but we use Go. And we like to use Go. It's really easy to implement the language. For transaction level simulation, it's still C or C++, but if your performance is not a big concern, then some people even use Python to run simulation, or MATLAB. Okay, so since we're talking about simulation, like especially we're talking about timing simulation and functional simulation, then those are something that you should also often hear about the difference. Now, on one side, we have functional emulation, right? Or sometimes we just say it's emulation. On the other side, we say timing simulation or just simulation. So what's the difference between emulation and timing simulation is if we care about the execution results to be exactly the same as a real hardware. So you probably, heard about, say, a game console emulator. They would call it an emulator because they would use your computer to emulate the functionality of your game console, right? But they do not achieve the exact same performance. Probably your emulation is much faster than the game console itself. So that's emulation. So for GPU or CPU, this type of digital circuit, we consider, say, this is the program, right? If it runs on real hardware or run on my emulator, we should generate the exact same result. Okay, so why is still useful? So we typically consider it's repeating the execution results of real hardware. Then we check the functional emulation, right? So we plug in a new algorithm. We first need to have an emulation there, so to guarantee, this can generate the correct output, so that my big program, my whole circuit can still work, can still generate the correct result. And it's also useful for testing software. So then sometimes you just don't have the hardware available, so you need to have some software emulation. So for example, there are lots of quantum computing emulator. So you probably don't have a quantum computer. In that case, use an emulator to emulate the result. Then also sometimes you want to generate traces. For example, memory access traces. You get a list of memory addresses, right? So these are the memory that I need to access in this order. Then you use this trace to feed into another like cache-only simulator that only care about cache. In that case, although it's not the best ideal scenario, but it can still provide you some information, and probably it can be faster than running a timing simulation that consider every component in your chip. Now on timing simulation, we need to repeat cycle by cycle detail because we want to tell that if this program runs on this hardware with this configuration, what's the execution time? So we need to predict the performance, and we need to predict the performance, and sometimes we need to predict the energy consumption. Then we need to examine detailed performance metrics. For example, cache hit rate, like what's the rate of a cache hit, right? How many transactions arrived at the DRAM? And we need to estimate energy consumption. Then execution traces, that we need to like take traces and to estimate the time. So, but for most of time, timing simulation, if you want to develop timing simulation, your program is data dependent. Like even most common program is data dependent. For example, if you have a loop, how many times you need to loop through this loop. Now you typically have a loop variable, right? If you need to loop through 100 times, then you have a int I equals 0, I is smaller than 100, I plus plus. Then you know that 1 and 100, you know, okay, it will loop 100 times. If you don't do functional emulation, your timing simulation will never know how many times you need to execute this loop and cannot provide a reasonable timing estimation of a program. That's why we typically need to feed in the data from a functional emulator, then to do data-dependent timing simulation and eventually get the timing result. However, there are still some cases we want to do time-only simulation. For example, in machine learning, that's a very typical case. In machine learning, most of the time we do matrix multiplication or convolution or softmax or ReLU or whatever, this type of predefined algorithms. In this case, just consider a convolution. Even if that's a black picture and a black convolution kernel, we still need to go through every element. Now, or multiplication, the times that we do multiplication and sum operation are exactly the same. In that case, we probably don't need to do functional simulation. We can have a reasonably accurate timing-only simulation. So in that case, in some particular scenario, timing-only simulation is possible. Okay, so that's time simulation and functional emulation. So later on, as we talk about Akita simulation, or then we'll see that Akita is mainly responsible for the timing part. Emulation part, you probably don't really need a framework. You can just implement it on your own. Okay, then another way to separate simulation, trace-driven and execution-driven. So last time we talked about execution traces. What is a trace-driven simulation? So trace-driven is a trace that we typically collected from a real hardware execution. Right? For example, if we know all the instructions that are executed by a CPU or by a GPU, we can print it in a file. Then we can feed in this file into a simulator. Then the simulator just replay all these instructions. Then we know we can have an estimation of the execution time. In that case, a trace-driven simulation is more likely to be a timing-only simulation, okay, without a functional emulation that is feeding in the execution instructions into the timing simulator. Then, so we can get a trace from execution, then real hardware execution, or we can get a trace from another simulator. Then it's really simple for development because you don't need to develop the emulator. The emulator can be really, really hard to develop because there can be thousands of instructions for a GPU or CPU, and you have to implement everything correctly. On the other side, execution-driven is a more, to me, is a more intuitive way, right? So we're emulating everything that is happening in a real hardware. So we integrate a functional emulator in the timing simulator. For real hardware, if it's doing add A plus B, now in our simulator, we just repeat add A plus B, right? We just repeat every action in a real hardware so that eventually we can get a reasonable timing estimation. So it's more difficult to develop, but it gets more accurate. Now for example, a very concrete example is spin loop problem. That is a very difficult problem to solve, almost impossible to solve for trace-driven simulation. What is a spin loop? It's this thing. Then if we have a program that will wait while A equal to 0, right? Just consider there's another program that will update A from 0 to 1. If that thread updates A from 0 to 1, then we can execute this thing, then eventually jump out of this loop, right? Or if it equals to 1, we jump out of this loop and do the real action. So while a equal to 0, it's a comparison operation, right? And there's a wait, it's probably a sleep or something, or some instruction in it. So how many times we execute in this loop? Then in trace-driven simulation, or trace-based simulation, we can only do whatever the trace is telling us. If the trace say execute this loop for 100 times, yes, we just do it 100 times. But if our hardware design is trying to say, oh, I can make things run faster and to make this core realize its value is changed faster, can you model this type of behavior change? Basically, you cannot. You cannot. You have to rely on the trace to tell you, oh, this is something that I executed. It's something I cannot change. But for execution-driven simulation, this is very natural. We don't have this problem because we're really executing on the other side, and we're executing cycle by cycle, that whenever this one can observe this change is basically depends on how soon this input register will get this value, right? So for execution-driven, this is not a problem. For trace-driven, this is a big problem. So even in recent simulator papers, I see that they have a hybrid trace-driven and execution-driven method, and their execution-driven only performs execution-driven in spin loop, this type of pattern, this type of programs. Okay, then let's talk about event-driven, or that's probably the last type comparison, like the classification of simulators. Cycle-based, like as we said before, if we pull every component, this component update, all of them update, then we move to the next cycle, then all of them update, move to the next cycle, all of them update. That is basically a cycle-based simulation. So cycle-based is typically very easy to understand and is easy to implement, but it also has some problems. So what's the problem with cycle-based simulation? Well, one major problem is, this is totally solvable, is multiple clock domain. So for example, in CPU and GPUs, a very common case is your core and your memory runs at a different cycle. They typically use something like a phase lock loop to synchronize them, or use a buffer to somehow synchronize these two parts. Like those are very analog circuit design, so that's not something we're talking about. But I just want you to know that a digital circuit can run with different parts, can run at different clock domains, right? Or these are two different components running at different clock domains. Sometimes even one component can change its clock domain, can change its clock frequency. This is a technology called dynamic voltage frequency scaling, or DVFS. So most of chips has DVFS today. CPU, GPUs, or any type of chips has DVFS. So for example, if you have a GPU in your computer, you don't want it to run at the full clock frequency and still your clock is ticking. You don't want it to happen because it's a waste of energy. So when sleeping, you want to put it down to the lowest energy. Then whenever there's a request that comes in, you can increase the frequency, right? Even for like booster clock, you can run to a much higher frequency, then go back to the regular frequency. So different clock domains. If you run cycle-based simulation, that means your incremental cannot be full cycles. You still have partial cycles to increment. Now, in that case, you probably want to have something like, say, if one runs at 1 gigahertz, the other one runs at 2 gigahertz. It's basically you always update at 2 gigahertz. Just for the 1 gigahertz component, you just don't update them every other cycle, right? So that is the typical way to do that. But if you consider if it's a non-integer ratio, then it's just make things really annoying. Another thing is long idle or wait time, right? For many components, then sometimes if you're running a lightweight program, if you're running only a single threaded program, your all other cores are waiting, they're not doing anything. And if you keep ticking everything, it will actually make your simulation really slow. In that case, we don't want cycle simulation. We don't want pure cycle-based simulation, because when they're idling, we want to fast forward to the next reasonable tick. Okay, now those are the problems with cycle-based simulation. So on the other side, we use event-driven simulation. What is event? It's basically we fast forward. We say, okay, at this time, we can predict what's gonna happen like 100 cycles later. For example, this memory read will take 100 cycles. Rather than tick, 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 tick until 100 cycles, we fast forward. We say 100 cycles later, we'll do this. Okay, that's an event-driven simulation. Then it's difficult to develop, right? It's much more difficult to develop, but it's more, the performance is higher. And in some other sense, even if I have multiple clock domain, or even something that happens outside the clock domain, it's very easy to handle with event-driven simulation. Now we'll see how we do event-driven simulation in Akita, hopefully in today's lecture. Okay, then because these two methods have their own advantages and disadvantages, more and more simulator is taking a hybrid cycle-based and event-driven simulation. But different simulators is hybriding them in a different way. Before I continue, let's just give you a quick overview, just some examples or some famous simulators that everyone is using. So how many of you have heard of Gem5? Gem5, right? So Gem5 is the single most popular complete architecture simulator today. So Gem5 starts from two simulators. One simulator is called Gem, one simulator is called M5. I think Gem is for the core side, M5 is for the memory side. So they combine these two together to make a simulator called Gem5. But today, you probably cannot tell it's actually combined from two different simulators together. It's the most commonly used simulator. It is a hybrid cycle-based and event-driven simulator that is implemented in a way that a component can still tick, 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 but can also schedule part of its functionality in the future. Then another simulator is called Multi2Sim. Anyone heard of Multi2Sim before? Okay, nobody. No, Multi2Sim. So, no, never mind. That's a less popular simulator. Then when I was PhD at early ages, I helped develop that simulator. But because of the leading developer is no longer working on that project is basically not maintained. So that takes a hybrid simulation method that is doing for the core. They think, oh, it's very common for the core to still need to tick, 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 right? But for memory side, it's more like every action takes a longer time. So the core side, the core part use cycle-based simulation. The memory side use event-driven simulation. Then Akita takes another different way to implement hybrid cycle-based and event-driven simulation. Akita is event-driven at the bottom, right? But 99% of the event are a special event called tick event. Okay, so we claim we have basically the same difficulty as developing a slightly more complex than developing a cycle-based simulation, and slightly lower performance than a cycle-based simulation. Okay. Sorry, slightly lower performance than pure event-driven simulation, and slightly more complex than a cycle-based simulation. Okay, we're taking the advantage of these two sides. So we're not going to talk about this today. We're going to talk about on Thursday's class how we can hybrid these two in Akita. Okay, so let's see some more concrete example in event-driven simulation in Akita. So this part, I'm going to basically read code with you to understand how this simulator is developed so that you can use it in your assignment. Okay, and my assignment is basically, next assignment is to use next month is probably the next after next one, is to use Akita to simulate a few simple sequential logic circuit. Okay. So time management, how we manage time. So Akita is a very unique design decision that we use floating point number to represent time. You may feel it's normal. Let me first introduce. This is a Go syntax, right? So all of you have used a Go in your first assignment. This is a type definition. We define a type. What is the type? It's called vtime in sec. What's the actual type? It's a float64. It's a type alias. It's not a type alias. Type alias has an equal sign. Then this is just a new type. But the fundamental type is still just a float64, double precision floating point number. What's the difference between a type alias and another type is type alias does not require casting. You can just simply add two numbers with vtime in sec number and the floating point number together without any problem. Then if it's a new type, you have to do explicit cast. Okay, so vtype in sec, this is shows a design or programming habit, programming philosophy that Akita is taking. So what is vtime in sec? So it tells you that this number is always in second. Okay, it's always in the unit of second. Don't ask it's a nanosecond, millisecond, microsecond, second, or hour or day. It's always in second. Okay, floating point 64 is wide enough to represent. Even if you have day level simulation, it's totally okay. Right? So vtime, what is vtime? V stands for virtual. And what is virtual time? So we have two different type of time system. One is real time, one is virtual time. So remember this sentence I said before. It takes 1 day to simulate a real GPU running a 1 second simulation, 1 second workload. Okay, so in this sentence, there are two time units. One is 1 day, one is 1 second. So which one is real time? Which one is virtual time? Which one is real time? So do you live in a real world or a virtual world? You live in a real world, right? So the 1 day part is the real time. The 1 second part, right? It takes a 1 day. So if we want to simulate 1 second GPU execution, it takes about a day. Right? If this is a sentence. Now our time is a day. The word that is being simulated is the virtual time. It's a virtual world. So that's a virtual time. That's why we say it's a virtual time. So it's a separation with real time. So vtime in sec is probably the most commonly used type in Akita. Okay, but it's basically a floating point number. So using this variable, we keep and say, oh, what is the current time and what the time that we want to schedule an event. Now, floating point time representation is a weird design decision. Most of other simulators use long integers on uint64. And also, when we talk about virtual time, we typically always start from 0. And it's just the start of the being simulator world. We typically start from 0, and it's always positive. So other simulators typically use a positive integer, uint64. Why? Because they count cycles. So their integer is a number of cycles. But I think same problem, multi-cycle problem, where even if something happens out of the cycle boundary, how we can deal with it. Then I think vtime in sec provides more flexibility, but also gives lots of problem within this floating point precision problem. For example, if I calculate current time is 3 nanoseconds, the next cycle is what? How you can calculate next cycle? I think that's a super simple thing, right? Sometimes I use this floor. Like say, current time is 3 cycles. 3 plus 1 and doing a sealing. Now we want to do a sealing to the next clock cycle, right? So let's slightly change it. If currently is 3.5 cycle, then we want to calculate the next cycle. Currently is 3.5 nanosecond. We want to find the next cycle. Next cycle is 4 seconds. So I do 3.5, 4.5. Okay, I cannot find a good example. Sorry. So sometimes it says 3 plus 1 and do a sealing. It can be either 4 or 3. Okay, because it sometimes can be 4.00001. Now if I do a sealing, it can go to a 4 or go back to 3. So, or it can be 3.999. So it's really hard to say, calculate exact the next cycle time. And sometimes because of this reason, I got stuck in the same cycle and do the same cycle again and again. So it's a very annoying decision. So it actually takes some extra calculation to prevent that problem. There's some drawback of using floating point as a time representation. But so far, after solving that problem, somehow solve that problem, we only have a performance issue. I don't think it's a terribly bad performance issue, so I'm accepting that one. Okay, so then Akita is a pure event-driven simulator at the bottom level. At the higher level, it may look like a cycle-based simulation, but at the bottom is event-driven. So what is an event? Event is an interface. And this is a Go interface of defining an interface. Then in assignment 1, I ask you to practice interface. So Go follows this syntax that is the same as this syntax. If you consider the type keyword, the new type name, and the actual time below, right? So this syntax is exactly the same. Type keyword, type name, and the actual type below. Right? The actual time is an interface. It has 3 functions. So for an interface in Akita, an interface in Go can only have functions, no implementation and no field. Okay, so it has an event defines a time, so when it can happen, and a handler who will handle this event, who will decide what's the action of the event when this event can happen. Then this is also different from other type of simulator that handler is associated with an event, each event. It's not associated with a type of event. It's associated with each individual event. For example, a tick event is so common that every component needs to have a tick event. So, but different components, different elements may handle this tick event in a different way. That's why we implement it in this way. Is secondary for now is not important, so let's skip this. Okay, hopefully we can have a chance to talk about why we need is secondary. Then for a handler, it's even simpler. We handle something, we handle this particular event, then it returns an error. And I rarely in my program, rarely return an error, I simply panic. Okay, so another thing that is the time manager, we call it an engine or event-driven simulation engine. So it manages the time going forward. So what is the key functions of engine? It can tell you the current time. What's the current time, right? It can schedule future event. If you give it the event, it will schedule an event to happen in the future. Then there's a run function. Run function, that means it will run all the events that are scheduled until there's no more event to run. Okay, so there's no parameter, just run. I tell you to run, there's even no control, say at what point you need to stop. It just keep running until there's no more event. Then pause and continue are straightforward, right? So simple interfaces. Then let's see how we implement this one. Or let's see how it works. So let's say we have a component 1 or handler 1. We can schedule the first event. We have to schedule the first event externally, so that when we call this run, if we do not have an externally scheduled event at the beginning, this run will immediately return because there's no event to run, right? So we have a run function. We call this run function after the kickstart event is scheduled. then this event, when we are handling this particular event, we need to say, oh, after this happens, something else will happen in the future. So we'll schedule future events, either to be handled by itself or handled by other components. Then this shuffling. Then we'll keep this chain of event will keep happening, right? Keep happening. Eventually, when there's no more event in this chain, we know everything is completed. Now we're done with the simulation. Okay, so the theory behind this event-driven simulation is as simple as a event chain. Eventually, this chain will stop. Then we're done with this simulation. I don't know if you have a question that if it keeps ticking, why can it stop? Yeah.
I have a question. So I think most simulators, like the timing system is like isolated from the scheduler. So basically, we don't really need to kind of complete all the events scheduled. We can like the engine or the timing system, it can update the time when we like complete the two events in the second tick.
Yeah. And
then we we know two events are completed, and we know there are some following events, and then so it's like we can like let the time increase in a finer granularity instead of these coarse granularity.
So we can let the time to go at cycle by cycle rather than go all the way to the end.
Yes.
Internally, yes, it is. We're doing that. So it's just the interface. Is a run will always run to the end, but internally we keep the time.
Does it always has a route for all the events?
It doesn't have to be one route. You can schedule. You can before the run function is called. You can schedule many events. So all this event will just take place when you call this run function. Okay, so a principle of Go is as simple as possible, to make everything as simple as possible. Then we try to keep this principle in Akita, although it's actually very hard. So the Go's creator Rob Pike once gave a presentation called, there's a keyword or sentence that is called "simplicity is complex." So to achieve simple interface is actually very difficult internally, that you can implement these simple interfaces. And for example, each secondary is something that I have to add. I cannot easily avoid. Later on, I can tell why it's necessary. So when we're done, then we typically say, oh, this is the total execution time of your program. Okay. So let's see an example. We see a very simple example. And this example is every line of code. I'm showing you every line of code. It's a cell split example. So what is a cell split example? We have one cell at second 0. We cannot start from 0. Now each cell is split between time 1 to 2, between 1 to 2 seconds after it was created. So say at time 0 we have 1, right? So a random time between second 1 and second 2 we split. So both of them are newly created. Now 1 to 2 seconds later, each of them will also split. Okay, so we keep split and remove this one. We don't need this assumption. Then how many cells do we have at second 10? I try to run at second 200. That's too many. I cannot finish my simulation. So I reduce it to 10, but that's a parameter. It's not important. Okay, so let's see a step-by-step guide about how to run this simulation, how to create this simulation. So what do? Is we first define an event, right? So since event is an interface, we just simply define this event, implement this event. And this event has nothing special. We call it split event. It has a time and has a handler, right? Now when we call time, we just return the time. When we call handler, just return the handler. Now when we call it secondary, it's not a secondary, it's a primary. event. Okay, any question? It's super simple, right? Then the second step, we need to create a handler. So how we can create a handler? Handler interface is also super simple. It only has a handle method. And so this is our handler. We define that as a struct. So the syntax is type keyword, the type name, and the actual type. Actual type is a struct with a bracket. And there's only one count. So we consider the whole word as all the cells as a count, as this handled by this handler. Okay, and we only care about the number, and we don't care about each individual cell. So then we implement this handle method. How we implement this handle method? It takes an event, right? Then return arrow, we never return arrow, we always return new. So what happens is whenever we split, we plus 1. So one cell becomes 2 cells. We add 1 more cell. Then we consider both of them are newly created. So we will schedule future events, schedule next split event. Because we predict when it will happen, so we schedule future event. How we can schedule future event? Then we do this. Schedule next split event. Then schedule next split event. We need a current time. So current time is provided by event.time, right? Event.time is always the current time that this event is being handled. This event happens at this time, so e.time must be the current time. So this provides the now field. Then in this now field, we first predict the time to split. Don't consider time to split left. Or how much time left, right? Then we do a random value. We do a random value that's a float point 64 and plus 1. Run dot float 64 will generate a random number between 0 and 1. And plus 1, let's say it's a random number from 1 to 2. We need to explicitly cast it to vtime in sec, so that is a second, right? Now we create this event. This event is current time plus the time left. The handler is always the current handler itself. So we provide this information. Then we say if the next event time is smaller than end time, we do engine.schedule next event. Now we say this thing will happen in the future. So it's the engine's responsibility to make it happen at that time. So there are a few global variables, like the rand, which is considered as a seed, is a global variable. What else? End time is a global variable, engine is a global variable. It's a very small program, so it's okay. Less than 100 lines. Okay, any question with this implementation? I think this event starts from one event. Now these events will explode, right? Will grow larger and larger, more and more events that will happen in the future. But no event will go beyond end time. If it's beyond end time, we just simply don't schedule it. Just assume there's no such event. Okay? So the last step 3, is to put them together. So remember we say these are the global variables. End time, we set it as 10. I tried 200, I cannot finish the simulation. Now there's an engine, there's a rand generator. It's actually here, you can use rand.float64. Why I use a rand gen there is I want to control the seed. Okay, rand64 will have a different seed every time. So here I have a rand gen. It's a way that I can have a control the seed. This is the program. I put in an example cell split. This is a particular way of a goal that is to be a testable example. If you put this program in a file called, say, cell_split_test.go, then your function is called example.cellSplit. It's considered as an example, both an example and a test. So when you run this program, when you run go test, it will run this test and see if it can get the correct result. Okay, so we need to, at the end, we need to specify what is the expected print message so that it can match if the actual print and is the same as the expected print. But here, the first line is easy. We create a new runt, then we create a source, which is a seed. This is 0. It's just Go syntax, Ghost library syntax. Then we use the seed 0. Okay. Then we create a new 0 engine. We do a 0 simulation. Then we can also do parallel simulation. And if you want to do parallel simulation, there's probably no point to run parallel simulation for this scale. But if you want to run parallel simulation, simply replacing this single line with new parallel simulation. Then no other changes is required. Automatic. Everything else is automatic. Now we create this handler. We start from one cell at the beginning. Okay. Then remember, before we call this run function, we need to kickstart this process by scheduling the first event. So here we schedule the first event. First event time is this time. It's basically the same thing as the previous line. Okay. Then first event is split event. Time is this first split time, and handler is h. Right. Here we need this ampersand representation. It's the same as C or C++. This get a pointer to this handler, this h. Get a pointer to get the address of this h, so that later on we can modify within this h. So then we call engine.schedule the first event. We schedule the first event so we can kickstart it. Then after this point, we call engine run. So just consider this chain of event will happen until there's no more event to run, which should be at the boundary of 10 seconds, right? So remember, this is the code that we write in the handler. Because of these 3 lines of code, we never run beyond the end time. Now at the end, after the run, we know cell count at a certain time, and the count is in this number. So this is pure C syntax, right? Printf syntax. Then here we specify output cell count at time 10 is 75. This is not useful. This is the test case specification. We want this line to print this thing, and it will really print this thing. If we don't use this particular source, it will generate a different final number. So that's why I start to force the source C to be 0. Okay, so every time it will run 75, and it's deterministic. Okay, so basically using less than 100 lines of code, we show a very simple example in Akita that only involves time management. Basically, there's no circuit simulation. Okay. Then I want to talk about honing error. What is honing error? So if you develop simulator, sooner or later you'll find sometimes your simulation will hang. Simulation hang means it either terminates too early, or it will never will keep running. Then in honing error, typically you can consider there are 2 types of honing errors. One is called deadlock. One is a live lock. What is deadlock? Deadlock means 2 things are waiting for each other and no one is making progress. Okay, no one is making progress. So in Akita, the most likely reason of a deadlock is you forget to schedule a future event. So your simulation is actually not completed. Your simulation is hanging there. So if it can be terminated early, but in MGPU Sim is a GPU simulator that uses Akita. Okay, in MGPU Sim, because we have other threads that are waiting for this simulation to complete, it will demonstrate a behavior of 0% of CPU usage, but your program will never finish. Okay, because we forget to schedule future events. This is deadlock. Deadlock will show this symptom that no one is doing anything because we're doing event-driven simulation. No one can make forward progress. Then another type of lock problem is live lock. So everyone is scheduled events in the future, and everyone will check, oh, what's the status? This one will check what's the status. This one will check the status. Then everyone is moving forward, tick, 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 but no one is actually making real progress. Okay, so in that case, you will find your CPU usage is still 100%, but actually very likely it moves very fast. For example, it takes a day to simulate 1 second execution, right? But in live log, you may probably take only a few seconds to simulate 1 second execution because they're not doing any real things. They're just tick, 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 and likely only 2 components are waiting for each other. So that's a live log. Deadlock is super hard to debug. Live log is super, super hard to debug. Okay. So there's something to be careful. Then you really eventually need some print break line debugging to eventually figure out the problem of honing error. Okay, so I want to talk about how engine works. We still have 9 minutes time. Let's try to talk a little bit about how internally how engine works. Let's read the code together. At least we can finish I think we can finish the zero engine part. So when we schedule an event, we push this is schedule function. We only talk about schedule and run function. Pause, continue is relatively easy. Schedule function, then the only purpose is to push it into the right queue. Now we have 2 queues. One is primary queue, one is secondary queue. Still, I don't tell you why secondary is necessary, but just tell you primary event goes to primary queue, secondary event goes to secondary queue. Okay, so we first do a sanity check. We get a null. So e.read null is the current read time. It's the current time of the engine. We encapsulate it in a read function because there's some like concurrency issue. We have to probably use mutex to log the current time. Okay. So now is current read null. We get the current time. If we want to schedule an event that is smaller than real time, we cannot go back time, right? We can only schedule future event. We cannot schedule past event. If we're trying to schedule a past event, there must be an error. Now, we would rather panic, make the program crash, rather than silently to allow this to happen. It will create more problem and even harder to debug. So this is a sanity check that we cannot schedule an event earlier than the current time. Okay, so if it's a secondary event, we call secondary queue.push, then we return, otherwise we push. So there's another demonstrate another philosophy that or coding practice in Akita that you like a beginner may write a code or undergraduate student at the beginning when learn like CSCI 141, they may like to write code. If event is secondary, you likely you may first do not is secondary, then do this thing, then else do that thing, right? We want to reduce the level of indentation as much as possible. How to do that? Now our rule is to rule out special cases on the top, then make the real logic happen at the end. You will see many more such examples later. Okay, not talk too much about this. Then run function. There are several steps. Then single run lock. That's to prevent that this run function from accidentally being run by 2 threads at the same time. We can only have 1 thread that's running the simulation, especially this is a serialized, like one event happened after another. Then there's a big for loop, right? There's a for something. There's no condition. Then it's basically equals while loop. While true equals true in other program language, or forever loop. So this is a forever loop, but with an exit condition. So if there's no more event, it's basically very easy to check. If the list has no event, then we just simply return, right? How we implement the pause is basically by competing a pause lock. So the pause function will take over the lock. The continue will release the lock. So it will guarantee that this will never collide with each other, and the pause will actually only return after all the events are completed. Okay, this is a pause lock. The comeback, then these are the real logic. We get the next event. Next event means the event has the smallest time value. Okay, quick question for you. what data structure that I need to use to store the events.
Meaning minor heap.
Yeah, max heap, right? We need we need to use a heap. It's a min heap. Yeah, we need to use it's the best thing is to use a heap. But sometimes for some reason, like in parallel cases, then there may be different options. But I'm currently using a heap. Okay, then we change the current time. So the current time, we also do a sanity check that we make sure this time will always go forward and never go backward. So double check at this point. Then we say right now is we change the current time so that the event time is the current time of the engine, right? So when later on when you call current time, it will always return this time. Right? This will make sure the event the time arrow will go forward. Then call hook. This hook is something we'll talk about later. It's basically a way that we can monitor, say what events are being executed. It's a whole system. Not important at this moment, but let's focus on these 2 lines of code. These are the real logic happens. We get a handler and we make handler.handle. We make it happen. Then this is a arrow, right? We don't care about the arrow at this moment. Basically, we never return an arrow. So if there's an arrow, it's simply panic in the handler. Okay, so handler, get a handler, then handler.handle, then make it happen. Okay, this is the logic of the serial engine, the run. So if you look at a simplified version, let's remove all redundant, that essential part. It's basically a forever loop that will take the next event, make the event happen until we have no more event to run, until we run all of them. Okay, this is the centralized time management part. And different from Gen 5, Gen 5 has an event queue per component event queue, per element event queue. Akita has a centralized event queue. Okay, then I think that's all we can talk today. And starting from next time, we're going to talk about how we can do parallel simulation.